Bismillahirrahmanirrahim. This is Pakistan International School Taif, and we are talking about the first year chemistry, the chapter number 3, and we are continuing the previous lecture, valence bond theory. In the valence bond theory, in the last lecture, number 24, I completed sp hybridization for the structure of beryllium dichloride. Now we are going to start the structure of acetylene or ethyne according to sp hybridization. Just continuation from the previous lecture. Sp hybridization means one s atomic orbital intermixes with one p atomic orbital, 50% ratio of s and 50% ratio of p, to form equivalent two hybridized atomic orbitals is called sp hybridization. Now since you done the structure of ethene in the sp2 hybridization, so two steps are same, because carbon is going to be involved in methane carbon, in ethene carbon, in ethyne also carbon. So because of carbon is going to be involved, that's why it's the ethyne or acetylene. So first two steps are common. So this is the carbon, atomic number 6, electronic configuration 1s, 2 complete, and this is the 2s, 2 is also complete. So degenerated orbitals 2px 1, 2py1 and 2pz0, and you done in the same step, you done in the case of methane as well as in the case of ethene, because carbon same atomic number 6, so that is the general, or we can say common electronic configuration of the carbon. So this is the ground state. State. So I'm not going to repeat it because two electrons are here. So these two electrons show carbon is a divalent, but it is a tetravalent. That's why you should promote one electron from the 2s to 2pz. So that's why electronic configuration of carbon now will be 1s 2s 1, and in each degenerated orbitals 2px 1, 2py1 and 2pz1. So students, we promote, we shift one electron from 2s to 2pz. Now 1, 2, 3, 4 are the partially filled or unpaired electrons. So this is excited state. This is the excited state now. Now here the different, these two steps are common. These two steps are common for the methane, ethene, ethyne or acetylene. Now, in the previous lecture, there was a double covalent bond in ethene. Means in between carbon atoms, there was sigma bond and pi bond. And this is the only repetition for you that the hybridization process, is going to be only for the sigma bond. All kinds of hybridization, sp3, sp2, sp also. Sigma bond only formed by the hybridization. Pi bond does not form. So in the previous structure, 2pz we separate. This 2pz was not part of the hybridization. Same case in the acetylene, carbon hydrogen sigma bond, carbon hydrogen sigma bond. There is one sigma bond only is a rule, and the two multiple bonds are there. So 2 pi bonds are there. So students, there are 2 pi bonds, that's why 2py and 2pz, they will not participate in the hybridization approach. Only S and P, because we are talking about sp hybridization. Pi bond does not form in the process of hybridization. No. So that's why 2py and 2pz will not participate. Only step number 3, carbon atom number 6. This is a complete cation. 1s is a complete cation. Now 2s1 plus 2px1. This one. So they are going to intermix with the 1:1 ratio. With a 1:1 ratio, these are going to interact to give this is the sp hybridized and this is the sp hybridized. So 2. There are 2 hybridized atomic orbitals only. 2s and 2px, they are going to intermix. This is called hybridized state. So one carbon has 2 sp. One carbon has 2 sp, other carbon has also 2 sp. So there should be a 4 sp atomic orbitals involved in the hybridization process. Now the students want the formation of pi bond. Formation of pi bond, these 2py and 2pz which not participate in the hybridization approach, they are going to participate for the formation of pi bond. So these two unhybridized atomic orbitals 2py1 and 2pz1 participate for the formation of 2 pi bonds. So you know pi bonds are formed by the side-wise overlapping, lateral overlapping, parallel overlapping. So these 2 are going to be separated. 2py1 and 2pz, these are called unhybridized atomic orbitals. They are not involved in the hybridization process. So write down this one, then I am going to draw the structure of the acetylene, ethene, atomic number carbon 6. We are talking about the sp hybridization. 1s2, 2s2, 2px1, 2py1, 2pz0, ground state, and only 2 electrons are unpaired, so not sufficient, insufficient for the satisfy the valency of carbon 4. So one electron shifted from the 2s to 2pz. 1, 2, 3, 4 electrons are here, and this is called excited state. Dear students, then what happens? There are 2 pi bonds are present in the carbon-carbon atom. There is a 1 sigma bond. First bond ever present in the carbon-carbon is called sigma bond, and other multiple bond must be pi bonds. Okay. So that's why only the intermixing between the 2s and 2px take place to form sp with a 1:1 ratio, 50% percentage character of S and 50% percentage character of the P. So they are going to intermix by the hybridized process, and you will get the 2sp hybridized atomic orbitals. So I am repeating again that these 2sp hybridized atomic orbitals, these 2sp hybridized atomic orbitals are only responsible to form the sigma bond. 1, 2, 3 sigma bonds are going to be formed by the 4sp hybridized atomic orbitals. This is very important. You must remember this one. And these 2py and 2pz will not participate in the hybridization process. So students, you must write this one, and you have to watch the lectures very carefully. You know this situation. It's my duty to give some instructions forever for you, that you can see, because we don't know what happened, how the examination will be conducted, the procedure we don't know. That's why you have to concentrate in your study very well. Now structure. Ethyne. Or acetylene. Ethyne or acetylene. Now dear student, this is a carbon. One carbon, it has a 1sp. This is the one. Same carbon, it has another sp. Each carbon has a 2sp hybridized atomic orbitals. So each carbon is attached with one hydrogen. So this is the hydrogen atomic orbital, straight overlapping to form a sigma bond. This is sigma bond is formed by the overlapping of hydrogen, one s, one this one, this. Now you are seeing this is the sp hybridized for the carbon, and there is another carbon. You are seeing sigma bond is in middle. Here the pi bond, and also here is a pi bond also. So it means that for the formation of sigma bond, sp hybridized of this carbon and sp hybridized for the other carbon. They straight overlap to form a sigma bond. So this middle sigma bond is going to be formed here. Then there is another sp. I told you there are total 4 for the both carbon atoms. 1, 2, 3, 4 hybridized atomic orbital for the acetylene or ethyne molecule. So in the last there is a hydrogen, same. This is the hydrogen. Sigma bond is going to be formed 1s1 like this one. So students, there is sp sigma 1s1. So 1, 2, 3 sigma bonds are going to be formed. And you are seeing straight, linear. Structure of acetylene is linear, straight. And the angle is a 180 angle. If you see your book, there is a drum shape. There is a drum shape here for the preparation of the 2 pi bonds and 1 sigma bond, and carbon has also 1 sigma bond in between, and carbon hydrogen sigma bond and carbon hydrogen sigma bond. So structure is linear. There is a linear structure. Now students, this is the carbon, sigma bond carbon, carbon hydrogen sigma bond, and carbon, hydrogen, sigma bond. This is same. 3 sigma bonds you are seeing. Now each carbon has 2 partially filled unhybridized atomic orbitals. So these are 2 p's each unhybridized. This is the whole P. There should be no confusion that hybridized atomic orbital has a shape of this. Maybe sp3, sp2 or sp hybridized, this is shape. So when you are going to write this small, this is going to be vanished. This is not going to be considered. So that's why this is the whole P from top to bottom, top to bottom. So there is a sideways, straight, parallel overlapping between 2 pz atomic orbitals to form 1 pi bond above and below. Overlapping must be above and below because this whole P here. So this is a 1 pi bond is formed, but there are 2. So there is another 2py. There is another unhybridized atomic orbital with each carbon atom 2py. Yes, so there is a overlapping between the 2py and 2py. Above and below. So 2 pi bonds are going to be formed. Carbon, hydrogen, sigma bond, carbon, carbon, sigma bond, carbon, hydrogen, sigma bond by the hybridization approach, and 2 unhybridized atomic orbitals, each carbon, they parallel overlapping to form 2 pi bonds. So you can see the structure of the acetylene in your book, that it is a space filling model is going to be formed. Space filling model. If you see structure drum shape like this on here, like this. This is called a space filling model. It states that there are 2 pi bonds and 3 sigma bonds are going to be formed here. So students, written in your book also, 2s and 2p orbitals carbon atom intermixed to give a 2sp hybridized atomic orbitals, as I explained. There are 2 unhybridized atomic orbitals 2py and 2pz for each carbon atoms, and 2 sp hybridized atomic orbitals are responsible for the formation of 3 sigma bonds by the end-to-end overlapping already explained. The structure must be linear, straight by the formation of one angle between the carbon-carbon and hydrogen atoms, and unhybridized atomic orbitals 2py and 2pz for the formation of pi bonds perpendicular to each other, also perpendicular plane of 2 sp hybridized atomic orbitals. Now each carbon atom possesses 2 sp hybridized atomic orbitals, and they are going to overlap. They are responsible for the overlap between S and this is the S and sp. This is the S and sp. S and sp, and sp and sp. This is the S and sp sigma bond. This is the S and sp sigma bond, and between sp and sp, third sigma bond. So pi bond is going to be formed by sideways overlapping between the two unhybridized atomic orbitals. So that is why cylindrical shape is going to be formed. So dear students, this is the end of the valence bond theory. We completed all kinds of hybridizations. sp3 hybridizations we completed three examples: methane, ammonia and water in sp3 hybridization. In sp2 hybridization we completed the two examples again: boron trifluoride and ethene gas. In the sp hybridization also we completed two examples: beryllium dichloride as well as acetylene gas. So go to the exercises questions, also visit the Federal Board website and take out the print of the previous question papers. You have to solve them very well, because nowadays no school is there, you are not coming to school, you are staying at home, you have a lot of time to spend. So it is your duty to obey the instructions of all teachers, because we don't know the situation till. Now students, we will see there is another very important theory. This very important theory is molecular orbital theory. Molecular orbital theory, MOT. And just I will give the introduction, then in the next lecture I will explain each and everything for you. The molecular orbital theory developed in 1927 and 28 by Hurwitz and Milken, in 1929 by Leonard Jones. Now here is the end I am telling you. This molecular orbital theory is superior to both VSEPR theory and valence bond theory. The first advantage of this theory, I am telling you that this theory explains the paramagnetic nature in oxygen and other also elements really. And you done in the very last topic of the chapter number 2, the paramagnetic substances are those which are slightly attracted towards the magnetic field due to the unpaired electrons. And those substances which are weakly repel the magnetic field, these are called diamagnetic. So this theory explains the paramagnetism. So we assume that there is a linear combination of atomic orbitals. We know that sigma bond is going to be formed and new orbitals called molecular orbitals. Molecular orbitals are going to be formed from the atomic orbitals, which are characteristics of the whole molecule. The molecular orbitals surrounds two or more nuclei to the bonded atoms. Now, what's the definition of the molecular orbital theory? Listen very carefully, then I'm going to stop. Orbitals after combining linearly, form two molecular orbitals. Atomic orbitals after combining linearly to form two molecular orbitals. One molecular orbital is called a bonding molecular orbital, which has a less energy, more stable, more strong. Molecular orbital has a less energy, more stable, stronger one, perfect overlapping. Other molecular orbital is called anti-bonding molecular orbital. Anti-bonding molecular orbital. This anti-bonding molecular orbital has a higher energy, less stable, no perfect overlapping, weak bond. So students, bonding molecular orbital is a sigma bond. Anti-bonding molecular orbital is called a sigma star bond. So here students, I am going to finish, and you have to read very carefully the previous lectures, and this is the very important, these are all the theories are very important and many questions asked. Otherwise all other topics are very easy. Only these Lesper theory, valence bond theory and molecular orbital theory, they are very technical and you have to understand very well. So I'm going to stop here. Thank you very much. Tomorrow, inshallah, next lecture, I'll explain in detail about the molecular orbital theory. Thank you very much.